All right, and Christina will be talking about the panoramic survey. I'll let you read out your acronym, Christina, when you're ready.
Thanks. Yeah, thanks for the opportunity to talk about this survey. Panoramic is a pure parallel wide area near infrared legacy imaging survey with JWST for cycle 1. We are a small international team led by myself and Pascal Oche. And the motivation for Panoramic is to create a wide area tier for cycle 1, specifically to look for rare and red galaxies that require spectroscopic follow-up at 2 to 5 micron. And so the early discovery of objects like this is critical because given the finite lifetime of the JWST mission, finding these galaxies early means we can then follow them up in the limited number of cycles afterwards. Our pure parallel observing strategy is a really efficient way to map large areas without using a lot of telescope resources. And in addition to that, it also maps large or uncorrelated independent areas, which is really important for minimizing the uncertainties from cosmic variance for rare objects that we're targeting. So this is an overview of the panoramic survey design. So we are going to map out 150 independent Nircam pointings, so that adds up to about 0.4 square degrees. So this is 4 times what would have otherwise been mapped by the GTO plus the ERS deep field survey areas. We defined a minimum pure parallel requirement to be assigned a pure parallel observing slot. So that was, we wanted 1 hour of science integration split over 6 broadband filters, which is ends up being roughly 20 minutes per filter. So we get depths in the range 27 to 28 magnitude AB 5 sigma point source limits. So not all of our pure parallel slots will be only the minimum. Some of them will be longer pure parallel visits. And so when we get visits that are longer than 2 hours, we plan to add in the 4.1 micron medium band filter, which will help us to improve our photometric redshift performance. And an important part of these pure parallel observations is that there's no proprietary time. So this means that our data is public immediately, and this sort of enables community follow-up of targets that are discovered in the panoramic imaging as early as cycle 2. We expect that by cycle 2, the cycle 2 deadline will have something like 20 to 30% of our imaging already taken. But for sure, all of our imaging will be ready for the cycle 3 proposal deadline. So this survey design enables breakthrough science by discovering currently unknown rare and red galaxies. So this splits into 2 different science cases. So science case 1 is to look for the first star formation in galaxies forming at cosmic dawn. So this plot on the left is showing our 6 filter minimum survey design with some SEDs for galaxies above redshift 9. And so what you see is that our Nircam filters produce a self-contained selection for galaxies above redshift 9 where we don't need any ancillary data, which is important because we don't know a priori where our pure parallel pointings will be. So in principle, we can identify galaxies even up to redshift 30. Our second science case is to complete the galaxy census at redshifts 3 to 7. So right now, our current state-of-the-art surveys have a hard time identifying dusty and quiescent galaxies above about redshifts 3 to 4. So here on the right panel, you can see 3 example SEDs of galaxies at redshift 4 to 5 that are either dusty or quiescent, and their SEDs, given what the Spitzer depths of some of the deepest Spitzer imaging that exists to date, it's hard to distinguish and select galaxies at these early times with these types of SEDs. And so the colored arrows are showing our minimum survey strategy for panoramic. And so you can see that we're going to get really good coverage of the SEDs for galaxies like this, like these types, and we'll be able to select and sort of identify them and characterize their stellar populations pretty accurately. So science case number 1, panoramic is going to occupy sort of a novel parameter space relative to GTO and ERS programs. So we're hoping to detect 80 new redshift greater than 9 bright galaxies, so brighter than L star, and up to 10 above redshift of 12. And an important component of this is going to be that with panoramic, because of our independent pointings, we are expecting something like 10% excess uncertainty on galaxies around redshift 12 due to cosmic variance, compared to more like 50% for contiguous fields of smaller area. And an important part of this is that we're also going to be capable of discovering rare intrinsically bright galaxies at redshifts of greater than 10 should they exist. Right now there's open questions about intrinsically bright galaxies in the early universe. GNZ11 is an excellent example of this, where found in very small survey area and also very bright. It's unclear, this is much brighter and more abundant than expected from extrapolations from the luminosity functions and the model predictions. So it would be interesting to find out if these things are representative of early galaxy populations. So science case 2, completing the galaxy census of redshift 3 to 7. For quiescent galaxies, the abundances are totally uncertain right now. The model projections span something like 2 orders of magnitude above redshift of 4. Surveys that have tried to identify galaxies above redshift 4 find a wide range of abundances. Probably some of this is due to selection effects, but we're hoping to put better constraints on the abundances of quiescent galaxies and sort of chart their appearance through this formation era, because we think these things are probably the relics of the reionization era. So here you can see where we're expecting to get with panoramic. We're hoping to get, depending on the range of model predictions, something like 30 to 200 massive quiescent galaxies from this early time, and these will make excellent candidates for follow-up spectroscopy in future cycles. Another part of completing the galaxy census is looking at massive dusty star-forming galaxies. So in particular, we're very interested in these recently discovered dark galaxies, which are dark right now because our infrared imaging is not deep enough, but with JWST and this simulation is showing panoramic photometry in particular, we're going to put much better constraints on what the stellar populations of these galaxies are and better photometric redshifts. And so the ultimate goal here is to try to characterize their contribution to the cosmic star formation rate density above redshift of 4 and understand what level of star production is happening obscured by dust. So now that the cycle 1 allocations have been made, we have a better understanding of what the real panoramic survey will look like in terms of the cycle 1 parallel observation availability. So here on the left panel, I'm showing here the points show observations for cycle 1 that don't currently have parallel observations scheduled that meet our criteria for our minimum survey strategy. And on the right panel is showing the histogram of exposure times for these available pure parallel slots that panoramic could occupy. And so our minimum was 1 hour integration time per visit. But what you see here is that a lot of these pure parallel slots actually have much longer integration time, so with an average of about 4.4 hours. And so if you were to take this distribution of exposure times to sort of, predict what the panoramic survey will see, panoramic will actually be sort of the perfect self-contained wedding cake survey strategy. So this is a plot showing just a redshift 12 luminosity function constraint. So that blue histogram translates into this red curve. And so you see that we are going to have a large area of shallow imaging to sort of probe the bright end of the luminosity function and distinguish between different types of evolutionary models for the bright end of the luminosity function. But we're also going to have a range of observations and pointings with much deeper imaging to sort of also probe the faint end. So panoramic was designed to do these specific science cases as a self-contained imaging survey, but in fact, it's actually going to produce a wealth of ancillary science possibilities. We're expecting to detect something like 2 million galaxies from our 0.4 square arc minute, 0.4 square degree survey. This is the expected photometric redshift performance for our minimum survey design, and we're actually going to get really good photometric redshift constraints even without ancillary data, even for a lot of these, even with only 6 filters. So our photometric redshift performance will be sort of comparable to what there was for candles, and so we're sort of expecting to create a legacy survey with a wealth of other science possibilities enabled by the good photometric redshift performance. So panoramic the panoramic team is going to produce some publicly available data products from our survey. Our data is public immediately, but the science-ready data products will be coming out over the course of our survey. So we are planning to release science-ready image mosaics for each of our 150 Nircam pointings. We are going to create multi-wavelength photometric catalogs with photometric redshifts for each pointing. I forgot to mention that in the map of real parallel observations that we might take, some of those parallel observations will lie in well-studied ancillary or well-studied deep fields with ancillary data. And so some of our pointings are going to have also ancillary data in addition to the Nircam imaging. So I mentioned earlier that about 30% of our data is expected before the cycle 2 deadline, but we're for sure going to have all of our data set completed, and our plan is to get it publicly released in time for the cycle 3 deadline. And along with this, we plan to include stellar population modeling and structures, as well as characterizing field-by-field uncertainties. So one feature of our survey is that each pointing is going to be very heterogeneous. So there will be a range of depths, a range of filter sets, a range of dither patterns. And so it's going to be important in order to do census observations or census measurements to characterize the completeness and selection functions and how the uncertainties vary field to field. So along with this challenging data set, we're going to try to make an automated Nircam reduction pipeline software that can go directly from, can handle all of these heterogeneous properties and go directly from pixels to galaxy catalogs on a relatively unmonitored and rapid timescale. So this is just a summary of the panoramic survey. So we designed it to search for rare and red galaxies missing from our current galaxy census. It's going to be a large area-wide tier survey of 0.4 square degrees with independent pointings to mitigate cosmic variance. We have a minimum survey design that gets to depths of about 28 AB mag 5 sigma. And the real survey will create a perfect self-contained wedding cake strategy and yield excellent photometric redshifts for a wealth of ancillary science for 2 million galaxies. So, thanks.
And thank you very much, Christina. Let's wait a little bit for some questions. So please put your questions in the Slack channel.
So I can start off with one of the first questions that we have here is asking if there's any synergy with Euclid or Rubin, and I guess any other telescope as well.
Yeah, I think there will be, I mean, both of those surveys will create wide area imaging surveys. And so, I mean, ours is going to be a little bit, it's going to be smaller than those facilities, but I think importantly, we're going to have this 2 to 5 micron that won't be accessible by Rubin or Euclid. So, so I think it's important to do a wide tier survey now. But sure, I think there's going to be plenty of science overlap, and we may even having this 2 to 5 micron imaging may be important for sort of informing those later surveys that will be able to probe much wider areas.
I'll ask the next question. So regarding redshift greater than 9 bright galaxies, do you have any estimate of the contamination fraction for low redshift interlopers?
Yeah. Yeah, we studied this extensively while we were preparing the proposal. I think, so one of the things that we did was to try to integrate deeper in the bluer filters in order to try to minimize the contamination rate. I would have to go back and look at the original proposal to get some firmer numbers for you, but I can answer that question later, I think, in the Slack easily.
Okay, that would be great. That's all so far that's in the Slack. I'll ask one of my own. I was curious for the redshift, 4 to 5 quiescent sources. What do you think your stellar mass limit is for those?
Oh, so the simulations that I was showing was 10 to the 10.8, I think, in solar masses. I mean, our depths would get us down much deeper to probably 10 to the 9, but I don't know off the top of my head the sort of how well we can say whether or not they're quiescent at those mass limits or not.
Right. Okay. All right, well, thank you very much, Christina, for a great talk. If people have further questions, please put them in the Slack.